Hello, people of the 44Con. Oh, how are you? You well? Did you have a nice lunch? All right. So I'm Lars. I'm here to talk about a project that I'm currently working on involving radare2. Do you know what it is? Do you recognize this logo? How many people? Come on. Give us a cheer. Oh, yes, really? Cool. So for those of you who don't know what this is, it's a crazy project driven by some people in Spain. They make this super complicated hex editor / like open source version of IDA. You know, your disassemblers, your debuggers, your emulators, all that kind of stuff you need to do reverse engineering, which is what I do. So I primarily reverse engineer malware, and I make like automated solutions in order to basically analyze malware and sandboxes and that kind of stuff. So I've been doing this for quite a long time, like 10 years or so. But it's only just recently that I've started using or making use of R2. And I do really like it. So what I will talk about today is my project, which is basically that I'm trying to build a hypervisor type of debugger. Quite similar to how you would go about using, say, WinDebug for remote kernel mode debugging, but not quite. So I'm using this ability in R2 to extend its functionality through an I/O abstraction layer. So this means that whenever you're using like the debugging UI or whatever, and you like type your commands to say single step the CPU, then my plugin, which I call cdebug for no good reasons other than my hacker alias, will then just sort of do the job for you. So it's basically a debugger backend. Yeah. And similarly, when you want to read or write to memory and that kind of stuff, all of that work is done by the plugin that I'm making. Okay, so on the other hand, you have on the other side, you have my target, which is a Windows VM, where I personally tend to run malware in. So the idea is that the Windows VM is running under QEMU, which is making use of KVM. And there's no debugging mechanism at all inside the VM. That's the idea. So in order to do this, I'm making use of a bit of an ancient protocol called the GDB Remote Serial Protocol, which was designed, I don't know, 1,000 years ago. Basically, it's a serial thingy. So radare2 will be the GDB client in this case. QEMU will act as the server. And QEMU already has this functionality built into it that it can expose something called a GDB stub, which just basically speaks this protocol. And it's quite straightforward. If you want to single step the CPU, you send it just like a lower ASCII S, and you get like an OK back or an error message. The second thing you need as a debugger is to read registers so that you know where the instruction pointer is, where the stack pointer is, that kind of stuff. And some of the limitations in the GDB protocol is that some of the registers I need were probably not around when this was designed. So you do get some of the registers, but not all of the registers that I need. So I had to sort of add some extra registers to this protocol. And I'll talk a little bit about that in a minute. The more, let's say, critical sort of limitation to this is the way it's designed to read and write to memory. So first of all, the main, one of the problems is that you basically end up transferring large amounts of data over a network connection, which can be quite slow. And it doesn't really make any sense since I'm actually running my debugger on the same host as the target. So my Linux host is talking, it doesn't need to talk through the network to communicate with or to read with the memory of Windows. But also, it's meant to read and write to virtual addresses, which is a problem because whenever you change processes, the contents at whatever address, a virtual address, will change as well. And I intend to typically, the malware would typically spawn a lot of processes and inject code everywhere. And so I need to sort of inspect all of the processes. So a colleague of mine had this cool idea. He was working on a similar project. And he discovered a way to sort of make QEMU share the physical memory of the Windows host directly through like shared memory primitives in Linux, which is cool. So this means that instead of transferring large amounts of data over a network connection, you can basically just do a mem copy between two buffers, which is much, much faster. So this is what I'm using. Basically, you have two I/O channels. One will basically read the physical memory directly, and the other one would basically control the CPU using DDB debugging mechanism. So let's do some demos. This is a Windows 10 VM. This is my Linux host, and I'll run radar. So specify 64-bit debug. This is the name of the shared memory file, which contains the raw physical memory of Windows. Okay, so this is how radar looks. Can you see this, by the way? Is it? Yeah, cool. So you can see it's connected to shared memory, about 2 gigabytes of memory, connected to localhost. It detects the version, and it says that the current process ID is 4, and the current thread ID is 0. On Windows, the idle thread will always be TID 0. So from here, we can look around. So you can see that I don't know, has anyone ever done some remote kernel mode debugging with WinDebug before? Okay, so what happens is, when you sort of break into it, there's a mechanism inside the Windows VM that is waiting for connection. So it's continuously polling to see if there's like a WinDebug trying to connect to it. And when it connects, it will sort of take you to the safe place. So you will basically land on an interrupt safe place, which is meant for debugging. So with this approach, however, we will basically just freeze the machine whenever we connect to it. So wherever it is, we will break into it. So it's random, pretty much. But as there's nothing going on inside the Windows VM right now, then there's a high chance that you will break into the idle thread. And you can see that the instructions here is basically doing a halt, which is sort of just a way to power down the CPU and conserve, power. Yeah. So from here, to make it a little bit easier, I will load some symbols. Yes. First of all, do this. You can list all of the drivers on the system by using the DMM command. Also, if you want to know which driver you're currently in, you add a dot at the end of it. This is the radar syntax, which is fun. And you can see that we're currently in the hardware abstraction layer, which is a DLL that is being used by the kernel. So it's basically kernel, hardware abstraction, hardware. So let me load the symbols for HAL PDB, which I've downloaded from the Microsoft symbol server at that address. Let's type third try. And at the same time, let's load the symbols for the kernel as well. To make this cooler. Okay, cool. So we have symbols, which makes life a lot easier. So you can see that we are indeed in the hardware abstraction layer. We are in the... Don't do that. Okay, don't screw up my demo. Okay, anyway. So from here, we can single step. Single step a little bit. We figure out we are inside the kernel. Tra-la-la. We can step over and place breakpoints. And basically, this is intended to work just as a normal kernel mode debugger. And when we're done, we can let it continue. And the Windows VM just basically unfreezes and kind of carries on whatever it's doing. Okay. So let's talk a little bit how I do this. Basically, you saw in Radar, you're working with virtual addresses all the time. And this means that since I've had access to the physical memory, I need to actually do the translation myself. And this is sort of a simplified version of how it's normally done on x86 64, designed by Intel. So the thing is, there's two inputs. There's the virtual address, and there's the value of the CR3 register. Okay, so the value of the CR3 register will point to something called a directory base table, which is the first table over there. And the idea is that whenever you change processes, you also change the value of the CR3 register, which means it points to a different base table, which means the outcome of this process will be different. That's why you can have like the same address in multiple processes with different contents. So what you do is that you extract some indexes from the virtual address, which will give you pointers into like 4 various tables. From each of those, you will read the pointer to the next table, so on. And at the end, you get something called a page table entry, which may or may not be valid. Once you have a valid page table entry, it will give you the physical address of the page in memory, which is normally 4K big. And then you use the last few bits of the virtual address as an offset into that page. That's how it's done. But some of the challenges with this is that it can be a bit performance. There's a performance overhead, since you need to do like 4 physical reads every time you want to do a read, just for a translation, which is why this is normally implemented at hardware. But the thing is, and this is sort of where the CPU ends and Windows begins. There's also a lot of scenarios where you will not get a valid page table entry, which Windows makes use of. So basically, there's like the least significant bit, first bit. If it's set, it's valid. That will give you the page. If it's cleared, that means that the CPU, I mean, the hardware won't touch it. It will just like send the page fault back up to the kernel. Kernel will intercept it, and it will then have 63 bits to play with. This is the case. Basically, it can be paged out, just like a swapped file, if you, in which case there will be bits in there telling you like where to find the contents. So like the number of the page file, the offset. It could be like a demand 0 thing, which isn't really interesting. It's just saying, give me a like 4K of zeros. It can be in transition, which is kind of weird. It's the memory manager who has noticed that some page hasn't been accessed for a while, so maybe it's somewhere in between in memory and on disk, but it's actually in memory and it's actually valid, so it's not a problem. And the last thing is that I don't know. You need to go and search something called the virtual address descriptors. Okay, so this is where we need to start parsing Windows, like the kernel's structures in memory and that kind of stuff. There's a few very important registers on the CPU related to like these things. There's the FS and the GS base, which is normally in user mode used for the thread environment block. I'm not sure. Have you ever seen like shellcode and that kind of stuff on Windows using FS prefix, like 30 something? You can grab the it's basically parsing structures in memory in order to typically to find the address of a routine that it wants to call. And quite similarly in kernel, in kernel mode, you have a very similar concept of using the GS register in order to access a superstructure, let's call it that, called the kernel processor control region. And when you're in user mode and when you're in kernel mode, you're still using the same GS prefix, but they mean different things. And that's why AMD or Intel introduced something called the swap GS instruction. So whenever you go from user mode into the kernel, it will swap the values of those two. And I can show you where it is. Let's see, it's got it. Okay, so yeah, you can see this is basically whenever you execute a syscall instruction, call any API in Windows, you eventually end up doing a syscall, which will transfer transfer control into this function. So you see the first thing it does is doing a swap GS, so that the GS base register now points to the kernel processor control region instead of the thread environment block. It saves the user stack pointer. It will retrieve its own stack pointer. It will build this structure called a trap frame on the stack just to save some information. And down here, it will start accessing, this is the current thread, and sort of parse that structure and do things with it. So that's what I intend to do as well. Basically, I'm using the same thing. As long as I can manage to retrieve the value of the GS base register, which I've just added to the GDB protocol, because QEMU already has them, so we can get this super KPCR structure, find its thread. From the thread, we can find the process, and the process will have something called a virtual address descriptor root thingy, which you can see. If you remember from university, you might have seen a red-black tree. This is my attempt at illustrating it, which, I'll be honest, I didn't remember what a red-black tree was, so I had to Google it. But it's a binary tree. It's a self-balancing binary tree, basically. So the idea is that since this might happen quite often, it's supposed to be fast to search through it. So you can go like left, right, depending on if your value you're searching for is lower or higher, where you currently are. So that's what I'm doing. Basically, I have my target virtual address. I'll just traverse the tree. All of this is in memory, yes. And basically, each of the VIDs will typically describe something like an entire DLL, for instance, which means that each node in this tree would typically contain information about multiple physical pages, because most DLLs are larger than 4K bytes. So there's this array in memory containing something that Windows dreamt up, and they called it the prototype PTE. So you basically find the prototype PTE related to that target virtual address. You grab it, and then my next challenge was figuring out what on earth is a prototype PTE, which I struggled with for some time. And thankfully, there was a new version of the Windows internals book, 7th edition or something, it came out, and eventually, like some of the minor annoyances, I managed to get it working properly. And it was a bit of, I was going a little bit suicidal at the moment. Basically, if the valid bit is set, then the prototype PT is treated just like a regular PT. So you would just flip some bits over. Just basically, you get the address of the the physical address of the page in memory directly. And it can be a prototype bit set, which for some reason means that they just encoded the PTE in a different way. So you just need to figure out where the bits are and sort of put them together and then form a PTE from that and then get the page. And then just to annoy me even more, they also had something called a prototype pointer bit, which means that the prototype is a pointer to a prototype which has an encoded PTE, which will give you the page. So this is sort of my development cycle as I was doing this and sort of just struggling, and why isn't this translating, or why, I mean, typically this will happen for like shared memory, so in DLLs and that kind of stuff, it's used quite heavily. Funny. So yeah, big overview of my translation process. You do the first step with like the regular x86 stuff. If it's valid, you get the page. If it's paged out, you're pretty much screwed, but you do know the location of it, so you could, if you can access the disk somehow, you could read it, but I don't currently do that. Traverse the tree and do the craziness with the prototype PTEs. And that's it. Easy, no. Anyway, the good thing is that once we've done all this, I mean, it took me some time to actually get this code working and everything. So the good thing is that we can also use the same tree in order to get the full memory map of a process. So it's kind of similar. I mean, you walk the same tree, but instead of searching through the binary tree, you just recursively walk the entire thing. So you basically want to list, like, you get every node of the tree, which means you get all of the information related to a certain process. And in there, you find like the ranges, the start address, the end address, like the protection stuff. There's a tag in there. If you've ever coded Windows drivers, you might have used ex allocate pool with tag. It should give, if you don't, it doesn't matter. And there's information on the file stuff. So let me show you some stuff here. Just check. Cool. So what you can do is you can list processes on the system using DP. We can try, actually let's do something. Slightly simpler. Let's do this. We launch CMD. Okay. So we break it. We search for it. And now you can basically select it. This means two things. Basically, the DMM command now changes from listing kernel mode drivers into listing all of the DLLs. It's loaded. It's not very many with CMD. And you have the DM command, which is basically giving you the entire memory map of it, which is quite helpful. So for instance, you can see things like this, which will correspond to the PE header with like the header on having read access. It's like the text section would have read and write. Read and execute. So, anyway, next challenge is this. So, as I just showed you how you can sort of list all of the processes, all of the kernel modules. And this is actually kept in memory because the kernel needs to use this as well. The challenge is that it contains a lot of information that can be used if you want to, write your exploits. Typically like information leaks, such as the kernel's base address is in there. And I'm guessing that for that reason, they wanted to just encode it. But it's quite similar to the other stuff. Basically, again, it's the GS base register, which points to the KPCR. And if you look around in the symbol files, you can sort of figure out that there's a fixed offset always to this structure. So you can find it. But you need to decode it somehow, because both the process list and the kernel module list, I mean, they're pointers to a linked list. So we can have a look. Let's see. Where are we? KD copy. So this is a routine. I'm basically just disassembling kernel mode memory. So we're inside the kernel looking at this code. And you can figure out this has actually been used whenever Windows itself needs access to this structure. So typically, it would use it if you say, if there's a crash dump that needs to be written. Normally, that would include things like the loaded modules so that you know which driver screwed up. In any case, if you look at this, you can see it's first checking whether or not the block is encoded, which it always has been, at least on my Windows 10. It's then moving on to setting the size, which it wants to decode, and it's going into this loop. And if you look at this loop, you can see that it consists of an XOR, a rotate left, another XOR, a byte swap, and an XOR. So it's typical, like an obfuscation routine. It's just flipping bits around it. So the other thing you can see is that it's making use of something called a symbol called ki wait never, and a symbol called ki wait always, which is, I don't know what it is. Actually, I did Google it. Apparently, it's something that is randomized on boot every time. So there are two random values. And then they're making use of the address of this data block encoded stuff. So this is like a good example of how I'm using Radar as I'm developing stuff for it as well. So what I did was basically just figure this out and then have a look at this code. And then if Windows can do it, then so can we. Basically, that's the idea. So I re-implemented in C. So this is basically the same logic. It's not the easiest code to read, I agree. But you can see that basically there's an XOR, there's a rotate left with the line 3 and 4, the shift and the ORing with the opposite shift. Another XOR, built-in byte swap, and another XOR. So the funny thing was, actually I went back and found an article in a magazine called Uninformed, which I read it was released in like 2007. There's a few famous people, Scape and Skywing. They did a lot of research on like early patch guard stuff, if you're familiar with the kernel patch protection thingy, which is this obfuscated monster inside of the kernel. And I just figured out that it's actually using the same exact obfuscation algorithm 10 years ago, which is weird. I wouldn't, I don't know. It was just weird. Whatever. So, just check how I'm doing on time. Let's discuss something cool. This is a challenge of placing breakpoints. For the most part, if you look at how this is intended to work inside the GDB protocol, the idea is that the client, which would be us or me, would request to the server that the server should place a breakpoint at a certain address. So let's say we wanted to place a breakpoint. Well, let's do some Explorer or something. So the challenge is, but first of all, challenge is that QEMU will use the value of the CR3 register of whatever is currently running on the CPU. And I don't really control what is running on the CPU. So right now, I mean, the idle thread is running on there. So if I wanted to place a breakpoint inside some other process, then how would you do that? Okay, so QEMU needs to do basically the same translation as we do, more or less, in order to figure out where to place the breakpoint. So if you want to write the breakpoint somewhere, you need to write the bytes CC, which interrupt 3, to some place in memory. So I came up with this little trick. Basically, QEMU is using whatever is in CR3 currently. So if I can just basically enumerate all of the processes and figure out what the value of CR3 is for Explorer exe, I can just temporarily write this new value to CR3 and then request it to set the breakpoint and then just write it back, which works as long as the translation works. And the challenge here is that QEMU doesn't really know about all of the madness we did with traversing the trees and the prototypes and that kind of stuff. So if the first step of the translation process fails, then setting the breakpoint, well, yeah, you will not be able to set the breakpoint. Let's if we say we wanted to set a breakpoint at the entry point of Explorer exe, yeah, something like this. So again, there is the idle thread is running on the CPU. Our target is the Explorer. We can use a command called dr, which I invented, which will then insert the breakpoint. Okay, so this is, in this case, it actually works because the initial part of the memory translation works. If we wanted to do something that doesn't work, let's see, if we wanted to debug a new process, for instance. Let's say, hang on. This would be funny. Let's start IDA. So the problem is, if I wanted to do set a breakpoint in something that isn't loaded yet, one of the challenges is that I don't know its PID. It doesn't exist yet, so I don't know its PID. It won't show up in my list. And then I did manage to find a place in the kernel. Basically, where I wanted to break the kernel just before it's inserting the new process in the list so that I can play with it. So let's place a breakpoint just after this one. I'll insert object. Let it go. And then from the inside, start IDA. And it failed. Let's see. Why did it not break? Oh, okay. But it worked the second time. Okay. So we can see we did in fact hit our breakpoint. So we obviously saw the entire VM is frozen, just because that's what happened when you break the kernel. And then in our list, we should find IDA. Here we can select it. It won't have any modules loaded yet because this is very early in the process creation process. But it will have a memory map what is currently loaded already. So you can see it's loaded the main executable, NTDLL, both 32 and 64-bit versions of NTDLL. So let's say we wanted to place a breakpoint at the entry point of IDA. Oh. Seek to it. So again, this would be the example that shouldn't work. Exactly. So again, the breakpoint wasn't set because the translation process failed at the first step, because it's just like, it's so early that, I mean, all of the page tables and that kind of stuff hasn't been laid out yet. So which is a challenge, since QEMU doesn't know how to parse and do all of the crazy magic that was basically the Windows-specific stuff. But we can do crazy stuff, can't we? Yes. Since we can read it, we can also write to it. So, I mean, I could write an interrupt 3 myself. I mean, I could write the byte CC. The challenge is that currently how this is supposed to work is that QEMU will always, it will only give me control back if it knows about the breakpoint. So I might have to change something in there, but what we can do for now, at least, is to just make sure we know what we're doing. Here, yeah. Make notes of the bytes that I am just about to replace. So the first 2 bytes of this call instruction, which is on the entry point of IDA, you can do is write. Yeah, thanks. That could have gone wrong, wasn't it? Why did it explode? Because you can't type. What you can do is write X. Let's do an EBFE, which would be an infinite loop, right? So my idea is just to let the entire system continue, and then hopefully IDA will just spin and go crazy. Let's try this. Yep, spinning. Okay, break it. See where we are. We are in IDA. Yeah, so we are at our loop. Now, remember what those bytes were. I need to write them back. Right. It was E8, right? Not EB. Yeah, good. So this is like the sort of painful process I have to go through whenever I want to just debug a new executable. Currently, I need to make this simpler at some point. But we are here. I mean, there's still frozen IDA. We were on the entry point of IDA. And from here, we can single step. Also, another thing to notice, if you do the DMM command right now, or if you look at this assembly looks a little bit off. You can see some out instructions, and this is not good. If you look at this, you see there's like Windows and Windows 64. So it's just something to keep in mind that this is actually a 32-bit executable. So you should disassemble it as 32 bits and not 64 bits. Okay, so you can debug it whatever you like, and eventually just let it go, and then IDA should pop up in here. Cool. So that's pretty much where I am right now. I hope to continue developing this, and maybe back next year we're having some other even more crazy stuff. But there are some people I need to thank. I want to thank the entire team I work with in Norway, Symantec Norway team, especially Stian Myhre, which is the guy who came up with this trick that I showed you, where we can share the physical memory with shared memory, which is sort of this like minor thing, but I think it's a brilliant, genius thing. I'm not smart enough to come up with all that stuff myself, so it's nice to have some people around you. And the other guy, Baha Namne, for just always taking time to sit down with me and discuss Windows internal madness. And on the radar side, I'd like to thank Pancake, Defragger, the Lemon Man, Insider, and all of the other contributors. Thank you very much for listening to me about this crazy thing. Are you still awake? Do you have any questions?